Thank you, Anne. Okay, so this is joint work with 𝔽n2, also from Weizmann. And the first thing that I want to do in this talk is explain the title. So I want to explain what do I mean by low-degree polynomials. So we will have in this talk polynomials over a finite field f with many variables, n variables. So these will be multivariate polynomials, and f will be a finite field. And actually, I will concentrate on the field f2. Okay, so and this is actually what is written in our online paper, but we managed to generalize since then to other fields, to finite fields in general. And maybe if I have time, I will say how to generalize the results. Okay, so what's a polynomial? Let's give an example. So it's a sum of products with coefficient from the fields. So this could be a polynomial over f2. And the degree of the polynomial, well, I'm sure all of you know, it's just, I'm talking about the total degree. So we are just going monomial, each monomial, we are taking the sum of the powers. This will be the degree of the monomials. And the degree of the polynomial will be the maximum of all monomials. So in this case, the degree is 2. Okay, and we'll actually be interested in polynomials computing functions. So we'll think of the polynomial as a function, a Boolean function actually, from f2 to then to f2 in a very natural way. Simply we'll take the n field elements, plug them into the polynomial, and evaluate it. And we get one field element. And if we are considering polynomial with compute function, we can use the identity a squared equal a modulo 2, and we can eliminate every power above 1 to the power 1, right? We can, if we only are interested in evaluating this polynomial, xi squared is the same as xi modulo 2. So actually we can write like f prime to be x1 plus x2, x3 plus 1. So these two polynomials compute the same function, although they are not the same polynomials. Okay, and there is a one-to-one correspondence between Boolean functions. Okay. And multilinear polynomials. Okay, so polynomials in which the degree of each individual variable is at most 1. Okay. And we'll go back and forth with this one-to-one correspondence. Okay, so this relation is unique. Okay, for any functions, there is a unique multilinear polynomial. And if we are talking about fq, the correspondence is with polynomials in which the individual degree of each variable is at most q minus 1, because we can think of xq as the same as x. So we don't need to take powers above q. Okay, so this is just preliminary stuff. I'm sure you are all familiar with that. So we're talking about low-degree polynomials. So we'll think of the number of variables as very large, going to infinity. And we think of the degree as much smaller compared to this number. Okay, so for example, we'll think of n going to infinity and the degree being constant. And we'll want to study such polynomials, or the functions that they compute. And we want to show a structural result for these kind of polynomials. And let me say what the structures that we are interested in. Okay, so I'll define I define K and D. Okay, so this is a measure involving n and d. So n will be like the number of variables, and d will be the degree. So this is the maximum over all k's, such that for any function or polynomial of degree most d, there exists some vector u0 in F2 to the n and some subspace of F2 to the n. So I think of F2 to the n as a vector space of dimension k, such that f on the subspace with the shift u0. Okay, so I take the subspace, I shift it by some constant vector. So this is we call this an affine subspace. So we want f on this affine subspace to be constant. Okay, so what does this question involve? So think that you are given a function of low degree. So you want to find the biggest subspace, affine subspace, on which the function restricted to this subspace is entirely constant. Okay, so we're looking for a structure inside something which you don't know that it has some structure. Okay. So let's, for warm-up, consider the case d equals 1. So what do you know about this case? So what's k and 1? n minus 1, right? Okay, so let's do it slowly. So we need only to consider a function of degree at most 1, right? So how does this function look like? So you have a constant term and some linear term. And you want a very large subspace on which this function is constant. So it's pretty obvious what to do. You take the subspace, let's say this subspace. The reason that this is a subspace is because we define it using one linear equation, right? This is a linear equation. And it's obvious that f restricted to this subspace is simply the constant a0, right? So this is a very large subspace of dimension n minus 1. Okay, so this was warm-up. So, okay, what's kn2? Swastik? n over 2, right. Okay, so this is also like a very old result from the 1900s by Dixon. So in some sense, he says that up to, if you look at degree 2 polynomials, then up to our linear transformations, they are equivalent to the inner product function. Okay, so, and for the inner product function, okay, so I think I call this function the inner product function. So for this function, it is enough to set like all the odd variables to 0, and then we make this function constant, and this is dimension n over 2, and this is essential. You can't do better than that. Okay, so this was already known. So what else was known about this K and D?
There's a little more than that, right? That you can entirely decompose this whole thing, like decompose.
Yeah. So Dixon says that you can, like up to a linear transformation, you can write any quadratic function as this form. I mean,
No, what I meant was like the zero set of this polynomial can be split into n over 2-dimensional affine spaces, like completely decomposed.
Okay, great observation. So maybe if I have time, then I'm going to talk about partitioning the space. Okay, so yeah. So we have these kind of results also. Okay, so what else is known? So if you apply a standard probabilistic method, and you take a random degree D polynomial, then it's not hard to show that K and D is at most O of D times n to the 1 over D minus 1. Okay, so I have some constant which I'm ignoring here. So for example, for D equals 3, this will be square root n. For D equals 2, this will be roughly n. So we see that it's pretty much correct for D equals 2. Okay, so this is the probabilistic method. So this was observed in previous work. And a lower bound okay, so this lower bound was in the work of Tardosh and Barrington. I think from 1995. And they actually wanted to, they didn't consider this as the main question to figure out, but they did it like on the way. They showed this lower bound. And you might say that these are almost tight, but for example, for D equals a constant, there is a gap between these two. Right, because this is like for D equals 3, this is square root n, this is n to the 1/3. And we bridge this gap. We get a tight lower bound, which matches the probabilistic method. So let's just say that if D is greater than log n, it was also previously known that K and D is asymptotically behaves like log n, okay? And actually, something even slightly more precise can be said. So in some sense, we are only interested in the case where D is smaller than log n, because this is where interesting things may happen. And it's, okay, so I didn't say it, but it's obvious from the definition of K and D that it's like a monotone decreasing function with respect to D. Okay, so I can, so I think of this as D, and this was K and D. So for 1, it's n minus 1. For 2, it's n over 2. And it decreases. And here it's roughly log n. Okay, for big n's, it's roughly log n. Okay, so our result is that for D smaller than log n, K and D is at least O of omega of D times n to the 1 over D minus 1. Right, and this matches the upper bound from the probabilistic method, so we understand K and D for any parameter. Okay, so we will see this theorem in its full. And then there is one more word which I didn't talk about in the title, applications. So we will see application to the field of pseudo-randomness. We will see probably just one application, but there are several more applications in the paper. Okay, so we want to prove this theorem, and we will use two tools, which are very, very nice and not that complicated tools, I think. Okay. Okay, so the first tool that we're going to use is a derivative of a polynomial. Okay, so when we talk about like real-valued polynomials, everybody knows what is a derivative, right? But we are talking about discrete objects. So it's less obvious how to define this, but let's give a definition. So we have some function. And we have a direction y, which is a vector in F2 to the n. So we say that the partial, we define the partial derivative of f with respect to direction y as, okay, so this will be a function, new function, and it will be defined as fx plus y minus fx. Okay, this is the definition. So this may seem arbitrary, but what's nice about this definition is the following fact: that if we take a degree d polynomial and we apply to him this derivative, then the degree is decreased by 1. Okay, so this is behaves the same as derivatives of real-valued polynomials. Okay, so the degree of this function as a function of x's is at most the degree of f minus 1. And let's prove it by an example. So take the function x1, x2, x3. Okay, so now when we take the derivative with respect to direction y, so what do we get? We get x1 plus y1 times x2 plus y2 times x3 plus y3 minus x1, x2, x1. Right? And we think of the y's as constant here, and the x's as variables. So when we open this up, we get x1, x2, x3 plus some 7 other terms minus x1, x2, x3. And these terms involve at most 2 x's and several y's. Okay, so this is, as a polynomial over x, this is of degree at most 2. And this cancels out with this thing. Right, so we proved it by example. Actually, to prove it generally, it's pretty much the same thing. Okay, so what's nice about this operation? If we have a degree d and we apply this operation, we get a smaller degree polynomial. So why not do it twice or several times? Right? Okay, so if we do it twice, what do we get? Okay, you can do the calculation and see that you get this thing. Okay, so just implying this thing twice. And in general, okay, so I have these plus and minuses signs, so I don't like them. And now I'm using the fact that I'm working over F2, so everything will be plus. So if I'm taking like the kth derivative of f with respect to y1 up till yk, so this will be the sum over all subsets of the numbers 1 till k, f of x plus sigma I in s yi. Okay, so this is just like applying this operation again and again. And let's call this function g of x. So what do we know about the degree of g? But it's at most the degree of f minus k, right? Because we apply, by induction, we apply k times the derivative operator. Okay, so in particular, if we take f of degree k minus 1 and we take k derivatives, we get a polynomial of degree at most minus 1. So there's only one polynomial, which is of degree at most minus 1. It's a 0 polynomial. So we get all 0 polynomial. Okay, so this is like the first tool. And the second tool, I'll write it here. Okay, so the second tool is a very famous lemma, the Milo-Lipton-Schwarz-Zippel lemma. But we're using a slightly less known variant of it. So we have a polynomial of degree d. Okay, and we know that it's not it's a non-zero polynomial. Okay, and f is, there is some point on which the polynomial is non-zero. Then the probability that on a random point, okay, in f2 to the n, that fx is not equal to 0, this is at least 2 to the minus d. Okay, so the more famous variant is where the degree is much smaller than the field size, and then if the degree is d and the field size is q, then we get something like this. So this is a more famous variant, but in our case, we are talking about very small fields, so the degree will be higher than that. So we can't use this estimate. But the same, I mean, changing the proof a little bit gives this lower bound. So what does this mean? It means something very nice about low degree polynomials. If you have a polynomial which is of low degree and you know that it's not, there is one point on which it's non-zero, then you know that there are many points on which it is non-zero. You can interpret this as saying that the set of points on which it's non-zero is of cardinality at least 2 to the n minus d. Okay, so this means that like as long as d is far from n, we have many points on which the polynomial is non-zero. This is very useful. Okay, so now let's state, okay, so this is roughly what we want to show, but let's state it more precisely. Okay, so our theorem says the following. Let k be the smallest integer such that the following inequality holds. Okay, so slightly weird inequality. Then, for any function f on n variables with degree d, there exists some affine subspace of dimension k such that f on u0 plus u is constant. Okay. And let's just say why this implies the bound that we showed earlier on k and d. So roughly, when d is smaller than log n, then this is roughly like saying that, okay, so the highest term here, like the biggest term here is k choose d minus 1 times 1, and all the rest are negligible with respect to it. So it's roughly the same as saying that n is k choose d minus 1, and this is roughly as saying that k is, okay, so the minimal such k is this thing. Okay, so this is just like basic calculation. I won't do that, but we'll prove this this inequality.
That approximately equal to is actually approximately implies. That's it.
Yeah. Okay. Okay, and in fact, we'll show something slightly stronger. We'll show that for any u0, there exists a u. Okay, so maybe write it slightly differently. Okay, so you give me the point, and I will build a subspace around this point. And the proof is actually, I think, quite intuitive. I mean, how would you show that there exists a large subspace? So a subspace of dimension 0, you know how to show, right? Because it's just one point. So let's think of this as f2 to the n. And there are, I don't know, numbers here. And there is like this point u0. So I can find a subspace of dimension 0 around u0 for which it's constant. And then I will pick some direction. Then I will show that there exists a direction such that both u0 and u0 plus this direction is constant. The function is constant on this. And then I will find another direction. I will show that this cube, the function is constant on this cube. And then I will pick a direction one by one. And in the end, I have a subspace of high dimension on which the function is constant. So this is like in brief what we'll do in the proof. But
particularly, you're getting any value you want, 0 or 1. You can get a constant subspace whose value is constant value 0. And you can
yeah. Okay. Okay. So maybe. Okay, so we'll have this iterative process in which we'll pick these. We will pick basis elements for the subspace which we built. Okay. So okay. So we pick iteratively y1 up till yk such that f on u0 plus the span of y1 up till yk is constant. And just to make notations a little bit easier, so without lots of generality, let's assume that f of u0 is 0. So why is this without lots of generality? Because otherwise we can add a constant to our function and do the same analysis on the new function. And then we want to show that f1 on the subspace is 0. Okay. So we start by k equals 0. So it's just just span of nothing. So it's just a 0 vector. So we know that this is okay. Okay, so this is like the basis of our induction. And now let's assume that we already picked y1 up till yk, and we'll now want to pick the new yk plus 1. And we now want to pick yk plus 1. We want it to be linearly independent of the previous y1 up to yk. And we also want that f on u0 plus span of y1 up till yk plus 1 will be 0. Okay, so this is what we do, and we will do it. We'll be able to find such a yk plus 1 as long as the following equation, or as long as okay, so we have this equation, so we'll take the opposite of this. Okay, so as long as this star inequality holds, we will find such a yk plus 1. And why does this prove the theorem? I mean, we need to show this, but we are doing this iterative process, and when we will stop, when this equality does not hold. So this means that this inequality holds, and we have a very large subspace. Okay. So do I want to delete? Okay, so I'm going to define a set A. This will be the set of all x's such that f on x plus span of y1 up to yk is a constant 0. Okay. So by our assumption of our process, we know that u0 is in A. And what we'll want to show is that there are actually many points on the set A. And from this, we'll find the new direction, yk plus 1. So it's not trivial even to say that there is another point in A, right? Because maybe the way you define it, there only use it.
Right, u0 plus anything in the span.
Right.
Yes.
Yes.
What?
Yeah. Anything.
Ah, right. Yeah, anything in, yeah, you're right. So anything like u0 plus anything from the span of y1 up to yk is also in A. So, okay, so I want to show that A is of size bigger than 2 to the k. So, yeah, this is cool. So we will show this, and from this we will find our new yk plus 1. So how we may interpret this thing? We may interpret this as having 2 to the k equations. Okay, so we have for any subset of the numbers 1 till k, fx plus the subset sum of the yi's should be equal to 0. Right? This is just going over all the elements in the subspace. So these are 2 to the k equations of degree at most d, because f is of degree d, and the y's, we think of them as some constants. So f of x plus some constant is still a degree d polynomial, and this is a polynomial equation of degree d. Okay, so what we will show is that actually we can represent A as a solution of much fewer equations of a much smaller degree. And then this will show that A is big. Okay, so we'll also show this by an example. Okay, so let's take the case k equals 2. So we have a subspace of dimension 2. And we write A as a set of all solution to fx equals 0, fx plus y1 equals 0, fx plus y2 equals 0, and fx plus y1 plus y2 equals 0. Right, so these are 4 equations of degree d. And let's look at another set. B. So we'll define it with 4 equations as well, but the equation will be slightly different. Okay, so we also have 4 equations. So it's obvious that anything in A is also in B, right? Because all these 4 things are 0, and we take subset sums of them. On the other hand, everything in B, we know that these equations hold because, okay, obviously. And from these 2, we get this equation. From these 2, we get this equation, and from all 4 of them, we get the last equation. So actually, A and B are the same. And what's nice about this new representation of A? That we decrease the degree of the equations, right? Okay, so this is a degree D. Polynomial. This is a degree at most d minus 1 because it's taking the derivative with respect to direction y1. The same goes for this guy. And this is a degree at most d minus 2. So just by playing around with the equation, we got equations of lower degree. Okay, and to generalize this, let's take, okay, so for any subset of the numbers 1 till k, we take the new polynomial f subscript s of x to be the sum of all subsets of s, fx plus some yi where I is in t. Okay, and let me just give the correspondence between this and this. So this will be f of the empty set. This will be f of the singleton 1. This will be f of singleton 2, and this will be f of this set. Okay? So what's nice about these fs? So we know that by the definition of derivatives that the degree of fs is at most the degree of f, which is d, minus the size of s. All right. And now, right, exactly. So, yeah, so we don't even need to consider equations for which the s is bigger than d, because these equations will become tautologies, because the fs will be simply the all zero polynomial. Okay, great. So let's see this. Oh my God, I'll write it here. Okay, so okay, so we write now A as a set of solution to fsx equals 0. And by the example, this is this is exactly A, right? So what do we have here? As you said, okay, so we have K choose J sets of size J, right? Sets S of size J, and each correspond to a equation of degree at most d minus j. So we can ignore sets of size more than d because this equation will hold for any x. So we can write here that we are only interested in s's of size at most d. Okay, so now we have much fewer equations, like k choose d or k choose d minus 1. And these equations are of degree d. And now we want to express it as a solution for just a single polynomial, not many equations. So we just take the product of this thing. Okay, so we're going over all subsets. Just taking the product of all fs's. So what do we have? We have that x is in A if and only if all these are 0, which is if and only if all these are 1s, which is if and only if gx equals 1. Okay, so we get that. Okay. Now I reveal the lemmas that I'm going to use. Okay, so now we know that g is not is a non-zero polynomial, right? Because u0 is in A. So this means that g of u0 is 1. And by the Miller-Lipton-Schwarz-Zippel lemma, we know that okay, so we need to figure out the degree of g, but we know that if it is of low degree, there are many non-zero points. So the degree of g is at most k choose j d minus j. Right? I even don't need to take the subset of size d because they contribute 0 to the degree. Okay, so what do we do now? So I remind you that we had this star assumption. So under the star assumption, we know that A is of size 2 to the n minus degree of g. And under the star assumption, we know that this is at least 2 to the k. Right? So we are almost done. We showed that the A is of size 2 to the k. Let's show how to pick the new basis vector for our subspace. So this is fairly easy. So because A is bigger than that, there must exist some u such that u is not in u0 plus span of y1 up to yk. Right? Because this is a set of size 2 to the k, and this is, okay, u in A, sorry. And this is a set of size more than 2 to the k. Okay, so let's pick some u and take y k plus 1 to be u minus u0. Okay, so what do we have? Okay, so we know that f on u plus the span of y1 up to yk, this is 0. We know that f on u0 plus the span of y1 up to yk is 0. And now we can write u as u0 plus yk plus 1. Right, because of this. So from these two, we get that f on u0 plus span of y1 up till yk plus 1 is 0. Right, because the union of these two sets is simply this set. Okay, so we got a subspace of higher degree on which the function is constant. And okay, and yk plus 1 is linearly dependent of y1 up to yk because it's not in the span of y1 up to yk, right? Because u minus u0 is not in the span of y1 up to yk. Okay, so that's it. We are done. We proved the theorem. Okay. So now I want to talk a little bit about the applications part. Questions so far? So let me just say that it's not hard to generalize this theorem such that it will find a subspace if we have several polynomials. Okay, so we have like f1 up till ft. Each one will be a degree d polynomial. Then pretty much following the proof and just looking at t polynomials instead of 1, we can prove that there exists a subspace of dimension roughly this, such that all the functions are constant simultaneously. Okay, and this will be useful for our application. Okay, so I want to talk about several pseudo-random objects, which are called dispersers and extractors. So I'm going to define affine disperser, and the definition will look quite similar to things that we talked about in this talk. And it's not a coincidence. I mean, this was like the motivation of our work. So a function f, a Boolean function, is an nk affine disperser if for any affine subspace of dimension k f on u0 plus u is not constant. Okay, so we want a function such that on any large enough subspace, the function will not be constant. Okay, and this is a pseudo-random object. So in some sense, we can state our main theorem as in the language of pseudo-randomness, in the language of affine dispersers. So our main theorem can be restated as that if f is a degree d polynomial, then f is not n. Okay, so there's some constant here. Affine disperser. Okay, simply because there is a subspace on which f is constant, so it can't be an affine disperser. Okay, so why is this interesting? So it turns out that many constructions for affine disperser and for affine extractor were in fact low-degree polynomials, and this shows that there is a limitation for how good parameters you can get. So you want to get k as small as you can when constructing such objects explicitly. And this shows a limitation of that. On the other end, by what I said earlier, by the probabilistic method, there exists, okay, so there exists some f of degree d such that f is n. I don't know, something like this. Affine disperser. So we know that this is tight. I mean, you can't get better than that, but you can, by the probabilistic method, get something close to that. Okay. And now I want to talk about another pseudo-random object, which is called affine extractor. Okay, so I'm going to write it above this definition because it's quite closely related to this. Okay, so f is an affine disperse extractor with error epsilon if for any subspace, affine subspace u0 plus u of dimension k, we have, okay, so now we don't say that f is non-constant, we want something stronger than that, and we want the expectation of x's in the subspace of -1 fx. We want this to be smaller than epsilon. Okay, so what does this mean? It means that on any affine subspace, the function, big enough subspace, the function is quite balanced. The number of zeros and the number of ones is similarly the same. So this is a much stronger notion than affine disperser. And in fact, there are pretty big gaps between the best known constructions of affine disperser and affine extractor. We can build much better affine dispersers and affine extractors. And the application which I want to talk about is a reduction from building one to another. Okay, so okay, so if so I'm going to assume that you can construct an affine disperser, which is also a low-degree polynomials, almost an optimal disperser of low degree. I mean, something which is very close to the probabilistic method. Okay, so if f is a degree d polynomial and n okay, so there is some constant here. And it is an affine extractor, an affine disperser with parameters, with almost optimal parameters for degree D polynomial. Then it will be also quite a good affine extractor. Okay, so F is n d minus 1 over n to the power of d minus 1 over d minus 2 affine extractor.
That's bigger than n.
Sorry. Yeah, right, thanks. Affine extractor with error, let's say constant error, 0.1. Okay, and while we lose a lot when doing this reduction, get from n to the 1 over d minus 1 to n to the d minus 2 over d minus 1, for constant d, this is like n to the alpha, where alpha is smaller than 1.
It's not the other way around. That is, like, it looks like you're really assuming that it's not constant on these relatively small dimensional subspaces, and then you're saying over here that even on.
Yeah, I mean, this is a theorem. It's not like obvious. But
Okay. So, but the dimension you're analyzing here is better than on the left hand side.
yeah, I lose something on the reduction.
But doesn't that say that it's also a degree? It's also an affine disperser for higher k.
Yeah, but if you are affine disperser for dimension k, then you're also affine disperser for dimension higher than k. Okay. If you take larger subspace, then you will be non-constant on this subspace. Okay.
And it has to be that it has to be a degree D affine disperser for subspaces of dimension n to the 1 over d minus 1. This fact, like, it has to be a tight thing. The degree of the
Yeah, I mean, you have a little to spare. You can, if you have here k, then here it's k to the d minus 2. But I mean, if k is bigger than n to the 1 over d minus 2, then it's trivial. I mean, to be an affine extractor, n affine extractor is trivial. But okay. So I'm concentrating on this regime of parameters, but it's more general than that. So this is interesting because we don't know to build affine extractors. So the best known affine extractor is for k, which is n over square root log n. I think it's there are two works. There are of Shin Lee and of Yodayev. Which gets to these parameters. So for a constant d, this will improve on these works. Well, I don't know how to construct this, but at least have a reduction. Okay, for example, for d equals 3, it's like okay, for d equals 4, it's like n to the some constant. Okay, so let me just show you the reduction quickly. Okay, so we use a very powerful theorem by Lovett and Kaufman. So they say the following. So if we have polynomial of degree d, and it is also biased. Okay, so let's take f2. So the expectation of over all x's of -1 to fx is bigger than some delta. Okay, so let's say that we have a polynomial which is of low degree and also biased. Then there exists some function g from f2 to the c to f2, and there exists c function from f2 to the n to f2, such that, okay, the degree of these functions is at most d minus 1, such that f on x equals g on f1 of x, f2 of x, fc of x. And c is some constant depending on the degree and delta. I mean, if the degree and delta are constant, then c is a constant. Okay, this constant actually grows like very fast. So we can. So what they say is that you can evaluate like constant number of polynomials of smaller degree, and then combine them together using some arbitrary function g. Okay, you should think of this as g as some arbitrary function. Okay, so let's see why do we have the reduction. So we will prove it in the counter positive. We will show that if a function is not an affine extractor, then it is also not an affine disperser. Okay, so let's say that f is not an affine extractor. So what does this mean? I actually erased that. So it means that there is a pretty large subspace on which the function is biased. Okay, so here the bias is greater than delta. Okay, so there are more zeros than ones. So now let's concentrate on this, on f restricted to this subspace. This is also a degree d polynomial, and it has bias delta. So now we can apply Lovett and Kaufman result, and we know that you can write. Okay, so this is, let's say that this is u. So f restricted to u can be write as g of f1 up to fc. Okay, because it's biased and it's of low degree. And the fi's are of degree d minus 1. So now we apply our theorem for many polynomials. So what do we know? We know that there exists a subspace W, which is a subspace of U, such that all fi's are constant on this subspace. Okay, so there exists some subspace inside here where all the fi's are constant on this subspace. But this means that f is constant on this subspace, right? Because f is simply g of f1 up to fc. And if all of them are constant, then also g of them is constant. So here we have, let's say, all zeros. So we showed that if it's not an affine extractor, then with some related parameters, it's even not an affine disperser. Hence, we get the reduction. So there are several other applications which I haven't had the chance to talk about, but if you wish to know about them, check the online paper. Thank you very much. Yes?
How efficiently can you find this?
Okay, so we also have algorithmic version of these questions. So the main thing that you can do is you can figure out that actually many of the equations which we are talking about. So we wrote A as, okay, so we wrote A here. There's a set of solutions to all these equations. So many of these equations are actually linear equations. So we can use this fact to benefit a lot. And we have like a sub-exponential time algorithm to find the subspace. And okay, and if you only want to find a subspace on which the degree of the function decreases by just 1, okay, so if you started with a degree d and you want to find a very large subspace on which the degree decreases by 1, decreases to d minus 1. So this you could do in polynomial time with some oracle access to the function. I mean, but and it also appears in our paper. Yeah.
I'm not sure if you just answered it, but what's the complexity of this theorem? Is this constructive? Because you can check the bias pretty easily, like for a function f. You can check the polynomial f. You can compute the bias pretty easily using a language sampling algorithm. So, is it possible to find out this 𝔽n F1 to Fk?
So I don't remember exactly, but I think that you know more about these G's and Fi's. I mean, I think that the Fi's are derivatives and the G is maybe the majority function. I'm not really sure, but I mean it's more explicit than that.